orbital overlapping and covalent bond. Okay, that's what we were discussing last time. So I told you that there are two types of overlapping. One is called head-on overlapping. Okay, and the other is called sidewise overlapping. Okay. Now, head-on overlapping will result in sigma bond. It's called sigma, and this will result in pi bond. Okay, sigma bond is weak as compared to pi bond. Pi bond is stronger actually, right? How to draw pi and sigma bond? We need to see this also. The drawing of the pi and sigma bond is very important. So you need to be able to draw the pi and sigma bond also. Okay. If this is s orbital with another s, so s with another s. This is the head-on overlapping, and the result is a sigma bond. Okay. Then we have the sidewise overlapping. So this is a sidewise overlapping, and this is a pi bond. We call it a sidewise overlapping. Okay, I will join you within a minute, I think. Okay, it's fine now. This is sidewise overlapping now. The same sidewise overlapping can be shown in this way. Okay, you bring them very close to each other and you draw in such a way. Okay, so this is a sidewise overlap again, and this is also resulting in the pi bond. Are you clear with this?
Yes, sir.
Okay. So this is the concept of the covalent bonding. So when we talk about the covalent bond and we see a single bond, it's a quick recapitulation actually. Single covalent and moving towards triple covalent. And in the middle we have double covalent also. So the stronger one is, this is a stronger and this is weak. Okay, so weak one needs less energy, strong one needs more energy. The melting and boiling points, high MPs and low MPs. Clear with this? All the explanation is for this. Are we clear with this part?
Yes, sir.
Okay. So whenever we talk about the concept of the covalent bonding is classified in that particular way. Okay. The example of the single covalent bond is hydrogen versus hydrogen. It's a single covalent bond. Oxygen versus oxygen is a double covalent bond. Nitrogen versus nitrogen is a triple covalent bond. One thing you need to keep in your mind, pi bond is weaker than sigma bond, and the reason for that is that sigma bond is a head-on overlap and pi bond is a sidewise overlap. So sidewise overlapping is weaker as compared to the head-on overlapping. Okay. Okay, I'll move into your book once again. Let me see what else is there in your book. Question actually, we need to see this. What does it say? It says that suggest a reason for the following trend in the bond strength. What's the reason for the bond strength? Yani the question is that why carbon-carbon single bond is stronger as compared to silicon-silicon single bond as compared to germanium-germanium single bond. So for that you need to look into the periodic table. Okay. So in the periodic table, carbon is at the top, followed by silicon in the same group and followed by germanium. So what is happening to the radius, atomic radius? Increase. Okay. So when the atomic radius is increased, what happens to the bond length? The bond length is also increasing. Larger radius will increase bond length and this will decrease the force of attraction between the two atoms. Decrease in force of attraction between two atoms. Decrease the strength of the bond. Got the points? When I'm moving from carbon to silicon to germanium, actually I'm moving down the group. So down the group, the size or the radius is increasing, which is increasing the bond length and decreasing the strength of the bond. So less amount of energy is needed to break this bond then. Are we clear?
Yes, sir.
Okay. Moving on to the second part. Question number 2. It says the fluorine-fluorine bond in fluorine is much shorter than chlorine-chlorine bond in chlorine, and yet it is much weaker compared with the energies. If you can see 158 and 242. Suggest a reason for this. So what can be the reason for this one now? I want you to think for a while and get a reason for that. Keep in mind, fluorine is much more smaller as compared to chlorine. Okay, but the negative charge on fluorine or the electron which are bringing to this much bond length, there's much more repulsion between fluorine atoms then. That repulsion is pushing those two atoms apart from each other. So fluorine bond length is there, absolutely it's short, but the repulsive force is pushing them apart. That's why it's making the bond weak, right? So when the bond is weak, the amount of energy needed is less delta E needed for it, okay, or energy or delta H. Are you clear with this? It's already on the repulsion, right? So there's a strong repulsion between fluorine as compared to chlorine. That's why the bond is getting weaker and the amount of energy needed to break a weak bond is less. Question number 3. Suggest a reason why the sigma bond between the two carbon atom in the ethene molecule is stronger than that of pi bond. Sigma bond is a head-on overlapping. Head-on overlapping is a kind of physical connection. Okay, that's why it needs more energy. It's exactly between the two carbon atoms. And sidewise overlapping is not touching the orbitals actually. They're not touching the orbitals. That's why they're far apart from each other. So the amount of energy needed to break a sigma bond is just like to break a shorter bond length, and for a pi bond the bond length is a little bit bigger than the sigma bond. That's why less amount of energy is needed for it. And pi is weaker than, when less amount of energy is needed, it means it's weaker. When more amount of energy is needed, it means it's stronger. I'll be repeating these points again and again, dear students, so keep that in your mind that these points are very important. Okay, let me repeat once again why sigma bond is stronger and why pi bond is weaker. In terms of bond length, sigma bond is shorter as compared to pi bond. Sigma bond is a head-on overlap, pi bond is a sidewise overlap. Head-on overlap is a kind of physical connection between the orbitals, and sidewise overlap is having a distance between the orbitals. So the two orbitals, when they are very close to each other, they need more amount of energy to be separated, and the two orbitals, when they are a little bit away from each other, like they are standing sidewise and just the magnetism is felt to each other, then they need less amount of energy. The more the distance, the less is the amount of energy. The less the distance, the more is the amount of energy. The larger the radius, the less is the amount of energy. The shorter the radius, the more is the amount of energy needed. Right? So bond length is actually the distance between the nuclei of the two atoms that are covalently bonded together. That bond distance is actually important. The shorter the bond length, the stronger is the bond, the more amount of energy is needed, the higher is the melting and boiling point, and vice versa. Any question?
No, sir.